Many real-world systems involve pulleys, which are just a wheel pinned in place with a rope or a cable running over it. And real pulleys always involve some friction because the shaft that that wheel rides on is experiencing its own little internal resistance to motion. But in systems with large forces at play, that friction is often so tiny that it can be neglected. So we're going to focus on frictionless, well, I got sloppy, sorry, pulleys. And we can always draw them like so, as a wheel with a cable running up and over them like so. In every pulley system, especially a frictionless pulley, the cable that passes over the pulley transmits the entire load from one side to another. And so what that means is that in a frictionless pulley, the tension is the same on both sides of the pulley, T1 here, T2, and what we know is that T1 is equal to T2 for a frictionless pulley. This holds true no matter which direction the two sides of the cable are pointed. And also what you want to remember is that the forces in cables are always aligned with the cables themselves. It's impossible for a rope or a cable to support a load that doesn't point in the exact same direction as the cable. That's a really helpful piece of information because if we know where the rope or the cable runs, we know the direction of the forces that it experiences. Only the magnitude becomes an unknown. One way of looking at it is that the job of a frictionless pulley is simply to change the direction of a force. Pulleys change the direction of a force. So, for example, here is a pulley, and hanging from that pulley, a cable going up and over the pulley, is a weight. This other side of the cable could come down to wherever we want, and maybe it attaches to, so let's just say, a simply supported beam, which looks like a thing on a pin joint and a roller like so. If we were to draw a free body diagram of the pulley, what we would discover if we picked, say, X and Y to look like this, is we would have the tension pulling down like so. That same tension would be pulling off at an angle that matches the angle of the pulley here, or of the cable. And then we'd need some reaction forces to hold this thing in place, so we could call that, say, Ry and Rx. Now I drew this as a circle with a little bit of offsets, but I don't want you to think that this is creating any moments. This is just a point mass. It's just nice to look at it so the arrows don't all end up on top of each other. On the other hand, if we wanted to draw the free body diagram of the beam here, we would have the reaction forces at both ends of it, and we would have an applied load that looks like the tension in that cable at the same angle as the rope. And by the way, if you did a little bit more analysis, I think you can see that that tension is simply equal to the weight. One of the other neat things is that pulleys can multiply forces. Pulleys can multiply forces. So let's look at this a little bit more closely. If I draw a pulley and it just has a simple cable running up and over it like so, we now know that the tension in this side is the same as the tension in the other side. And what that means is if we give a reaction force here that we call, say, Ry, you can see from a quick sum of forces that Ry is going to be equal to 2 times T. Well, we could flip that upside down and take advantage of it. Think about this for a second. If I have a cable running like so, and riding on that cable is a pulley that has, say, a weight hanging from it, and I pull up on the cable like so with some tension T, the free body diagram for the pulley looks like the tension from both sides of the cable and the weight going down. And so if I do a force balance on this, what you'll see is that 2T is equal to W, or if we solve that for the tension looks like W over 2, which means I can pull half as hard to lift the same weight. And it's not completely free. If I were to pull up on that rope, I think you can see if I pull 1 foot of rope out, that pulley is going to slide around until 6 inches of it came from both sides of the pulley. In other words, I pull a rope 1 foot up, but the weight is only going to move 6 inches. So I have to pull twice as far, but I get to lift twice as much. We can get even fancier with this, by the way, if we wanted to. So imagine instead a system involving these 2 pulleys attached to each other with a weight hanging from them. And now what I could do is I could run a single cable that comes around the bottom. Whoop, let's change colors, make this a little easier to look at. I'm going to come down around the bottom wheel, up over the top one, down around the middle wheel, and then up. And let's just go over one more like so that now you could imagine actually grabbing this end and yanking on it with the tension T. If I draw a free body diagram for the double pulley system here, what you will see is that we have the weight acting down, but now we have 4 cables, and all 4 of them have the same tension in them. In other words, that force balance would tell us that 4 tension is equal to W. In other words, the tension is equal to W over 4, and I can now lift over 4, excuse me. And now I can lift something 4 times as heavy with the same amount of effort. So, how do we solve pulley systems? Anytime you see them, all we need to do is isolate the pulleys and draw the free body diagram. And remember, the forces always align with the cables. And then we get to follow the same solution strategy we've been using the whole time. Free body diagram, then we write our force balances, then we solve the geometry, and lastly, we work out the algebra to find the thing that we're actually after. And if you follow these steps, it's always the same. So really the new thing that gets added when you start thinking about pulleys is just what the free body diagram looks like, and it can be a little counterintuitive that you actually need to put the tension on there twice, pointing in the direction of the rope or the cable on both sides of the pulley.